What's up, everybody? This is again your resident chemist slash teacher Mark, and today we will be talking about gases. So this is a two-part series because of this length of scope. We will first, in this part, the first part, we'll discuss a brief introduction of the gases, how gases exert pressure, the laws encompassing the properties of gases, or what we call the gas laws, and how this experimental resorts, the experimental data that conceive the gas laws can be combined into one ideal equation, which is what we call the ideal equation, the ideal gas equation, and applying that ideal gas equation to a mixture of gases. So let me get my pen. I'll be right back. So gases are the least condensed phases of matter. This is because there are, unlike solids and liquids, the condensed phases of matter, there are little to no intermolecular forces between this between the molecules or atoms of a gas. So because of this simplicity, their state or their situation can be described by three parameters, namely pressure, volume, and temperature. When we say state or situation, it's like something that describes what they're in right now. So, for example, there are people in the room. There is a room containing 30 people. So you ask, "Kamusta sila? Kamusta tong sitwasyon nila? Are they too cramped inside the room? Is the room too hot for them, or are they pushing each other away, or are they pulling others towards them?" So that is what we call the state. So the quantity, or in the context of chemistry, the number of moles is not considered a parameter that describes the state of a gas here. It's because it just gives you the quantity. So for example, when you ask someone, kamusta to sila sa kwarto? Kamusta to sila sa kwarto? You don't say tat 30 to sa kabilo, right? Because that does not answer your question of what is the state or the situation the people in the room are in right now. So ang munang analogy that. Next, we discuss how do gases exert pressure. So if you see in the slide, pressure is defined as the force applied per unit area perpendicular to the force. So how do gases apply force on an area? So if you see in our what do you call this? If you see in our slide here, the gases here move freely, right? And since they move freely, they will have a velocity. And when they hit the surface of the container, if you see in the slide here, they will apply a force, and that force is, and the perpendicular component of the force perpendicular to that area is what we call the pressure. So let me show it to you in an illustration. Okay, that's it. So here's our board. Oops. I'll just minimize this one. Nope. Oops. No, I'll just minimize myself now. Okay. So here, this is our board. So let's say let's give this a closer look. The diagram in our slide. So we have, this is our surface of our container, right? So we have a gas particle moving in an indefinite direction. And while it moves, there are chances that it will hit the container here, right? And it will bounce towards this one by Newton's law of motion, by the Newton's laws of motion. Now, when it hits here, it will apply a force here to this particular area surface with area A. So let's say it hits here, right? The force. Now, if you can see, the force is not perpendicular. It's not exactly perpendicular. And since it is a vector quantity, the force will have an x and a y component. So let's say this is our y and this is our x component. And it has an angle theta here. Okay? Now, we know that, what do you call this? We know that from our as you can see here in our diagram, this one is the one this component of the force is the one directly perpendicular to the area that it hits. So by nature, pressure is equals to force over area. And since only the perpendicular component, and since by definition pressure is force per unit area perpendicular to the force applied, so this is the only one considered to be applying the pressure. So it will be Fy over A. Now, on our trigonometric functions, f sub y is equals to f cosine theta. Substitute this one here. So your pressure therefore will be force F cosine theta over A. Amo na siya. Okay? Then we erase this one. Now, since the since atmosphere is practically a layer of gas above the surface of the Earth, that means the air also exerts pressure towards it. And we know in our high school science that the pressure exerted by air is 1 atmosphere, which is equivalent to 101,325 pascals. But how is the pressure of the gas measured here? Now, remember, so how do they measure the mass of the gas here? So let's say we have, this is the sea level, or let's say this is the surface of the Earth, which is what we call the sea level, the average surface of the Earth. Okay, and this is the edges of the atmosphere. So this is the edge of the atmosphere. And let's say we take a square column, similar to what we call, in our language, what we call a dos por dos type. So this column has a base which is shaped like a perfect square. So the dos por dos gid saya, it would look like this. And the area of the square is equal to, 1 square meter. Or it is a square na 1 meter by 1 meter, right? Now, going back, pressure is equals to force per unit area. Now the major factor the major force that acts on our atmosphere that holds them together, holds them here not to escape, into outer space is the gravity of the Earth, or the gravitational force. And remember that Newton's second law of motion, force is mass times acceleration from Newton's second law of motion. Now, since the governing force acting upon the air is the gravitational force, the acceleration becomes the g, or the gravitational acceleration. So, therefore, change board ta. Therefore, the pressure of the atmosphere is equal to the mass of the column of the air that we have shown here, multiplied by the gravitational acceleration, multiplied by its area, which is 1 meter. So, since it is 1, anything over than 1 is the same number. So this is our what do you call this? This is our atmospheric pressure, which is the mass is, this is the mass of the air. Okay. Now it was, and that's how we get the 1 atmosphere, or the 101,325 pascals. Remember that Pascal is the SI unit for pressure. However, when we're dealing with the properties of gases, we usually use atmosphere as the standard unit for gases. Okay. Now the atmospheric pressure is 1 atmosphere only at sea level. Now, when you notice, when you go higher, going back here, when you go higher up, above sea level, let's say you're trying to climb a mountain, you're at the summit of the mountain, you notice that the height of this column also decreases. Height decreases with increasing altitude. Now, since the height of the height also decreases, that means the mass of the air from where you're situated, from the higher altitude up to the edge of the atmosphere, also decreases. Will also decrease. That means since pressure is directly proportional to the mass, that means that the pressure of the atmosphere decreases with increasing altitude. And that is also, you notice, the air gets thinner when you go up on the mountain. So this is one result of that, because the atmospheric pressure decreases with increasing altitude, because the amount of air that you feel also decreases as you go up, as you go higher above the sea level. So next we will discuss naman gas laws. So now that we have discussed how gases exert pressure, now let's try to see what happens when we exert pressure on a gas. So let's have a setup here, the classic piston cylinder setup. So when you say, so here the gas is inside a cylinder. If you can see both in the graphics and in our PowerPoint presentation here, we see that the gas is inside the cylinder and it is sealed shut with a piston. So the piston can freely move up and down the cylinder. However, the rest of the cylinder does not, the other walls of the cylinder do not move. So this is the one that only moves up and down. A piston. Now we place it in let's say a water bath that maintains the temperature constant. Okay, since the cylinder is completely sealed by the piston, that means the amount of gas present in the cylinder remains also constant. So we have these conditions here that the temperature remains constant and the number of moles or the amount of gas remains constant. And let's say that the gas occupies a volume V. And since it is under the atmosphere also applies a pressure onto the piston, which we name as P1. Okay? Now let's say we add more pressure here at P1. So what will happen? Now since you're adding force onto the cylinder, common sense dictates that you will squeeze the piston down, which in turn decreases the volume. Sorry. They're on the same size. I'm really sorry about that. So let's just put this in graphics. So this in turn will decrease in size. So you can add additional pressure by, let's say, pushing the cylinder, the piston down, or as we can see in our PowerPoint presentation, by adding weights, which will apply force onto force onto the pressure, which pushes the piston down. As you can see here. Now the volume Now, the volume here actually decreased. So, the relation is V2 is less than V1, okay? Now, obviously, common sense dictates that it will obviously decrease because you're trying to squeeze the gas together. Siyempre, ma-decrease ang volume ng occupy nila. But by how much? Now, certain physicist named James Boyle, I forgot his nationality, tried observing the change in volume with respect to the temperature, and he observed that the pressure is inversely proportional to the volume. And this was further replicated and held true, and these collections of experimental observations, what do you call this? Where this collection of eventually accepted into a law, which is what we famously call the Boyle's law. Now, from our diagram here, and we only have the relation. So how can we make this relation into an equation that we can actually work on? Now, since the temperature and the number of moles are constant, we collectively make them as the constant K. In order to make this relation an equation, we apply the constant K here. So that would make pressure is equals to K over V. That means K is equals to PV, right? Now, supposing that, now since the initial pressure and the volume is equals to K, that which is equal to the temperature, and the number of moles of the of the gas, then that would also follow that this K is also held true to P2V2. So that means we can get the equation P1V1 is equals to P2V2. So that's how Boyle's law works. Now let us proceed with what will happen when we use temperature. We go to the next is we go to the Charles law. As you can see, Charles law, it shows that the temperature of the gas is directly proportional to its volume. So this explains that when your balloon is exposed under the sun for too long, it will burst because the gases become hotter in there, and according to Charles' law, so as the air inside the balloon gets hotter, the volume occupied by the gas will also expand, which in turn will expand so much that it will burst. Now, we'll reserve the molecular interpretation of the gas laws when we go to the kinetic molecular theory. What we need to know for now is how do we use this gas law? Is to familiarize ourselves with the gas laws and how to use them in problem solving. So next is the Gay-Lussac's law. So remember, since pressure is inversely proportional to the volume, I was lost in transition. Now, since in Gay-Lussac's law, or the Amontons law, officially known, I don't know why they call it Gay-Lussac, because obviously it was the guy who discovered this law was not named Gay-Lussac. It states that the pressure exerted by a gas is directly proportional to its temperature. So this again was actually collected from experimental data, just like what James Boyle did, or the one who discovered Boyle's law, formulated Boyle's law. Next is the Avogadro's law. This is pretty straightforward. So obviously, when you increase the amount of substance obviously more matter means it will occupy more volume. This is pretty straightforward. So going back in the Charles law. In the Charles law, oh sorry, I did not turn on the. Okay. Now, in the Charles law, remember that since temperature is directly proportional to volume, that means you hold also other factors constant. So that would be pressure and the number of moles. Right? Now, so this will be collectively described as a K. So again, in order to make this one a constant equation, so you apply your constant K. So T is equals KV. Now let's say we have an inflatable balloon here we have a stretchable balloon here containing air. which weighs containing air under atmospheric pressure. And syempre, because the balloon is sealed rather, the number of moles remain constant. So it is a temperature. It is under a temperature T1 and a volume V1. So you heat the balloon and it will expand, right? It will expand to a volume V2. The same under atmospheric pressure, and the seal is held tight. Now, based on our relation here, so that means T1 is equals to kV1. The same way, T2 is equals to kV2. So, transpose so that the constants are on the one side of the equation. So T1 equals to, where V1 is equals to K. Similarly, T2 over V2 is equals to K. Substitute this one to the other and vice versa, and you get the relation for our gas laws nga T1 over V1 is equals to T2 over V2. The same relation you also apply both in the Gay-Lussac's law and the Avogadro's law. Okay? Wait lang. Okay, I'll pause this, guys. I'll be right back. Okay, I'm back, guys. So let's have a recap of the laws that we have reviewed so far. So Boyle's law, we know that pressure is directly proportional, rather inversely proportional to the volume. Charles' law, wherein the temperature is directly proportional to the volume. Gay-Lussac's law, or the Amonton's law, wherein sorry guys, my cam is not that stable, so Please bear with me. No, that's not what I want. Oh. Oops. Sorry, it's a bit wobbly. That's it. So in Gay-Lussac's law, wherein the pressure is directly proportional to the temperature, or rather, the temperature is directly proportional to the pressure, and the Avogadro's law wherein the number of mole is directly proportional to the volume. Yeah, that's it. Now, this seems rather confusing. Since this seems rather confusing if you memorize this all laws, but from the observation of that eventually were accepted into laws, a unifying equation can be made based on these relations. So, okay, pressure is directly proportional to. So since pressure is directly proportional to inversely proportional to volume, when you transpose this, it will be PV, right? Now, since volume and the pressure are directly proportional to the temperature, they will also be. So that means PV will be directly proportional to T. And since volume is directly proportional to T, obviously it will be directly proportional to P. So it will look like that. Now, in order to this to become an equation, we insert a constant. So this becomes, inserting a constant, this will become the famous PV is equals to nRT, which is our. Okay, this is such a killer. Wait. Which will be our. Oops. It's tilting, guys. I'm so sorry. Oops. Which will be our. Oh no. The ideal gas equation. And now, as you can see, the value of the R, which is our gas constant here, is 0.08206 liter atmosphere per mole Kelvin. Now, there are different values of R. R is not just a gas constant, but rather it's a constant. It's one of the constants that are universally ubiquitously used in physical chemistry and thermodynamics. However, for the purpose of describing gases, we'll be using this gas constant at 0.08206 liter atmosphere per mole Kelvin. Okay. Now I'll pause this one to fix my camera, and after that we will go back to our gas mixtures. Okay. Yeah, so before we proceed to gas mixtures, I would like to introduce a new concept with you, which is the molar volume. Now, the molar volume, is by its name, is simply the amount of volume, is the amount of space or the volume that a gas occupies per 1 mole. Okay, it's just like your molar mass. Like for your molar mass, it's the mass of 1 mole of a substance, while molar volume is 1 mole of the volume occupied by 1 mole of an ideal gas. So the ideal gas is what we are the ones that follows faithfully follows the gas laws and the ideal gas equation. Now, if you see in the slide that if we have a mole of a perfect gas at 273.15 Kelvin under a pressure of 1 atmosphere, so that means it's at sea level, the molar volume of the gas by manipulating our PV equals to nRT is 22.41 liters. And these conditions that yielded the molar volume of 22.41 liters, that is liter per mole. Okay. I would like to remind you guys that the unit for the molar volume is liter per mole. Now that means, if you see in the slide here, that 1 liter, that 1 mole of that perfect gas under 0 degrees Celsius and 1 atmosphere has a volume of 22.41 liters. And that value is what we call the standard molar volume. It's a standard molar volume. And so all gas, regardless of their identity, when it follows the ideal gas equation, has a molar volume of 22.41 liter per mole under the conditions indicated here, which is 0 degrees centigrade and 1 atmosphere and a pressure of 1 atmosphere. Now these conditions are what we call the standard temperature and pressure, or STP. That is the STP of a perfect gas or an ideal gas. So ideal gas and perfect gas are completely interchangeable. Also since STP is hard to obtain, particularly the T part, it's pretty much hard to attain. So there is another convention, thermodynamic convention here, which is this SATP, or standard ambient temperature and pressure, wherein the pressure is 1 bar, or approximately 1 atmosphere. It's just slightly lower than 1 atmosphere, and the temperature here is 298.15 Kelvin, or 25 degrees Celsius. So we use 25 degrees Celsius because that is a temperature where all all constants related to chemistry, or all intrinsic properties related to chemistry, were obtained. So that's it. So now we proceed to a mixture of gases. So let's say we have, I'll erase this one. Now let's say we have a mixture of an ideal gas. Say we have a container here, and that container is airtight. So that means that container is airtight and very durable, so that means it has a constant volume. So let's have this one here. Let's have these molecules. So let's say it is composed of 3 gases. The container contains 3 gases, namely, so let's say this is gas A, this is gas B, and this is gas C. Okay? So they are under constant volume, and let's say they are again under a water bath. Inside a water, they are submerged in a controlled bath, a controlled temperature bath. That means the temperature is constant. And again, since this is tightly sealed, no gas or air, to be more specific, can come in and out of the container. So the number of moles is constant. Now, since gases exert pressure, that means this gas mixture will exert a pressure of PT, right? Okay. Since this is a gas mixture, so obviously it will have a total number of moles of MT. Now, assuming that the gases do not react with each other, and that all of them are completely adheres to the ideal gas equation, that means the total number of mole of gas in the mixture in the container is equals to the sum of the number of moles of the individual gases present there. It would look like that, okay? So guys, remember that going back to our ideal gas equation, PV is equals to nRT. So that means N is equals to PV over RT. Now, we substitute each of these expression of moles into this one. Syempre, with respect to their their respective subscripts to indicate that is for gas A, gas B, or gas C, or for the whole gas mixture. So this would become PT is equals to PT V over RT is equals to. So since these three gases do not interact with each other, each of them will exert their own pressure. So for gas A, it will exert a pressure PA V over RT. So this is because remember that their volumes will be the same because they are in the same container. Remember that a gas occupies the shape of their container, okay? So these are so remember that here, that since this is constant, so since we have indicated that volume, temperature are constants, and syempre, ideal gas constant by its name, these are constants. So that means the volume and temperature of A is equal to the volume and temperature of B and equal also to the volume temperature of gas C. So we can exclude this out. So this is because this becomes their common factor. So this will be right? So change bar. Sorry, I said to change bar because it does not fit. So it would look like that. Now, going back here, we can move this one to the other side of the equation. And if we move this one to the other side of the equation, this expression here and this expression here will cancel each other out. Right? Thus, the final expression will be and this is our Dalton's law of partial pressure. Okay? Now, similarly, the same goes with the total volume of the substance if the gas mixture are held constant, as you can see here below, and that is what we call the Avogadro's law of partial volume. I will not delve deeper into the derivation because the derivation is pretty similar to that here, to that for the Dalton's law of partial pressure. Okay, now we will introduce another quantity, another property of the substance, or I cannot say this is a property. Let's say another quantity na lang of the gas, which is what we call the mole fraction. Now, mole fraction simply is just the number of moles of the gas divided by the total number of moles in the gas mixture. It's just simple as that. So, if you remember mole percent, when you say mole percent is equals to the number of moles of the component or the substance divided by the total number of moles in the mixture times 100. Amo na ang mole percent, right? Now, mole fraction, you just remove the 100 and that becomes your mole fraction. Okay? Now, going back to our derivation here, we go back here, today. So, so we know that here, this is, let's say PT is equals to PA plus PB plus PC. We go back to our mole fraction. Okay? So, and we have stated that sorry. I'm lost in transition, guys. Sorry about that. Now, given this gas mixture, since the total number of moles is Na plus Nb plus Nc, and mole fraction of A is Na over Nt, so that the same goes with the mole fraction of B. That means that when you total the mole fraction, the mole fraction of all the gases in the mixture is equal to 1, right? So we relate so we go back to our mole fraction here, and we use again the ideal gas equation. From here, we substitute the N to this one here. Okay, so we do that. Which is equals to P1, PA V over RT all over PT V over RT. So, cancel. Therefore, I will erase this one. Therefore, we can prove that the mole fraction of A is equals to the fraction between the partial pressure of A over the total pressure of the gas mixture. So, we can say that partial pressure is equal to the total pressure multiplied by its mole fraction. Gets you, guys? Of course, you won't answer because this is a vlog. I'm so stupid. Sorry about that. Now, I'll end here. This ends our part 1 of our discussion for gas. I will post what do you call this? I will post some question. I will post how to solve some what I find difficult questions difficult problem-solving questions relating gases. I will post it later on my vlog. I don't know what will be the name, but nonetheless, don't forget to click the I button and subscribe. Okay? See you